So this is what we call a DPM, as I told you. And when we are talking about DPM, we are not specifying the neural net, that mu network, that mean network, to be anything specific. Yeah? So you can think about anything, right? One question from my side: what is the dimension of the output, this mu t? What is its dimension? Same as? Data sample, right, exactly. So this is why, for instance, you might be interested in using UNet, right, or one autoencoder, right? Because autoencoder has this property: you're going to get your data, right, and then you're going to give you back the same kind of data structure, right? So it's autoencoder. It just wants to do the denoising for you, right? And what you are doing eventually, you're taking one noisy version of data. This is the same data structure. And mu t is going to be the same data structure as x, right? That guy goes in, that guy comes out, right? But in DPM, we're not specifying the architecture, okay? But one particular architecture, which is very popular nowadays, is DDPM, denoising DPM. And why denoising DPM is interesting? Because, I mean, first day when they proposed it, I'm not sure if they went through all of these details. Probably they ended up through another way with that architecture. But eventually you can show that this is basically one specific architecture. But the key point is that everything that you need to compute is like readily seen, or readily, you have good quality samples when you want to just compute that sample loss in this architecture. So to understand this DDPM, let's just look at this particular posterior mean once again, right? So this is the posterior mean that we had. I told you that I'm going to simplify it later for you. So this is now the time. And what we do, in this architecture, as you see, right now we're thinking that we're taking x0, or data sample, and also the noisy one, xt. Both of them go inside this expression that we have here. So x0 is here, xt is here. So we're going to just do the computation, this computation. This is going to give us eta t, right? And this time we don't have any typos, so this is correct now. Okay? Okay. Now, one thing that I can do, that xt, how do I generate xt? I'm going to noise x0, right? So I'm going to get x0. I put it inside that expression that I have. So this is the expression for xt, right? So it's x0 and the noise term, right? So I sample some noise. I'm showing it by epsilon t. This is the noise that I sample for time t, right? One noise. This is just an output of a random generator. Now, this is going to be xt, so let me just replace this xt here, okay? I'm going to replace xt with this expression. Then this guy is going to just be left with x0 and the noise, right? Correct? So xt is just being replaced here. Now, the next thing that I'm going to do, I'm going to multiply the first coefficient with this one, add it up to this one, factor out x0, right? And again, I multiply this fraction with the second coefficient, and I'm factor it out for epsilon, right? So one thing that you can see, when I multiply this guy with this one, denominator is, this coefficient is the square root of the denominator, right? Right? Everybody sees that? This coefficient of the noise, square root of 1 minus alpha bar, is the square root of this denominator, right? So it's going to cancel out, right? One thing, okay? And then the rest of it going to remain the same. So if I do that, then you're going to end up with this expression, right? So as you can see, this guy divided by 1 minus alpha bar, this is this term, right? Plus this guy multiplied with this one, which is alpha bar times alpha. This is what I have under the square root. This expression, 1 minus alpha bar, t minus 1. And the denominator is the same, so I'm going to keep the same denominator, right? So it's a quite simple calculation, right? So, and this guy here that we have, as I said, this guy cancels out with this one remains only a square root, right? So now I'm going to call the first guy AT, the second guy BT, and I want to see whether I can write it down in a simpler form. Everybody's cool? Okay, let's go ahead and write it down. One thing that we do know is that alpha bar t, alpha bar at time t, is the product of all alphas from time 1 to t, right? We define it that way. So this means that if I have alpha bar t, I can write it down as alpha bar t minus 1 times alpha t, right? Because alpha bar t minus 1 is the product up to time t minus 1. Then I multiply it with alpha t. This is now the product up to time t, right? So I have this simple identity. Now I can use this to simplify everything. So this is the expression that I have for AT, the first term, when I open it up. Okay? So I'm going to take this square root out and this particular fraction out, and I'm going to remain with this term. Now looking at this term, what's going to happen inside the brackets? There is 1 minus alpha t, right? There is 1 plus alpha t, right? They're going to cancel out. And the last thing going to remain is going to be alpha t times alpha bar t minus 1, right? Which I can write it down as alpha bar t, right? So I can simplify it. It's going to be this guy. So 1 minus alpha bar divided by 1 minus alpha bar. They're going to cancel out, right? Everybody's cool? So they're going to cancel out. This is going to be a square root of alpha bar t minus 1, right? So that whole long term can be simplified in this form. And since I'm working at time t, I would like to have only time index t. So this is why I'm going to write it down in this form, but you simply see it, right? Just look at the above identity. Alpha bar t minus 1 is alpha bar t divided by alpha t, right? So I'm going to replace it. The whole expression is going to end up with this simple fraction. Everybody's cool? Questions? Okay, so that AT is quite simple. Let's keep it aside. And then let's go for BT. For BT, what I want to do, I had this particular expression. And now the thing that I'm going to do, I'm going to write down this square root of alpha bar to be, square root of alpha, the first term in the denominator. I'm going to write it down alpha divided by a square root of alpha. Okay? Everybody's cool? Now, I'm going to open up the term. So the next thing that I'm going to do, first of all, I multiply it. When alpha t gets multiplied to this term, it's going to be alpha t minus alpha bar is going to be alpha bar again. Now I'm going to add plus 1 minus 1. Okay? Cool? Now, next thing that I'm going to do, I'm going to factor out that 1 over alpha t, square root of alpha out. And now I'm going to just sort things out. This is 1 minus alpha bar. You see the first plus 1 with minus alpha bar. This is the first term. Minus, I have 1 minus alpha t, right? This is the red term, right? And denominator is as before. Everybody's cool? Now, you look at the blue terms. The blue terms are the same, right? The denominator is the square root of it. When I do the division, it's going to be a square root, right? And I am left with one other term, which again only depends on time t, right? So I can simplify it in this form. So 1 over a square root of alpha t is only depending on t. This is 1 minus alpha bar t. Again, only depends on t. And this is now a one extra term. Okay? Everybody's cool? Questions? No question? Great. So if you got no question, then let's go ahead and put them back inside the expression. So we said that eta, this was the posterior mean that we had. This is AT times x0 plus BT times the noise. Now I'm going to replace things here. The first one was square root of alpha bar divided by square root of alpha. This term is just, I replace exactly the one that I had. And I can simply factor out that 1 over a square root of alpha here, and then everything goes inside the brackets. Okay? Now, forget about all the math we did. Look at this expression, the one which I have just put something under. Right? There is a bracket under. What is that term? Look at it and tell me. Yes, and that epsilon that I have there, the red epsilon, is exactly the one which I generated to make my xt, right? I have not used any other noise, right? So when I wanted to write down xt, I started with the fact that I have this blue x and red epsilon, right? And I wrote things down. I ended up this one. Now this expression that you see, as you said, this is exactly x at time t, right? So what can I say? I can say that eta t is eventually this factor, xt minus one term. And that term is eventually depending on my epsilon, right? What is epsilon? This is important now to pay attention. What is epsilon? Epsilon is the Gaussian noise that I use to generate xt from no, x0. This is important. Pay attention. So this is the one which I wanted to indicate. Yeah? So I wrote down this form, right? I'm working with alpha bar. This is the direct link, right? So epsilon t is the one which I use in my training loop, right? In this guy, right? When I want to I just randomly sample one time instant, right? And then I want to know what is the noisy version. I generate one epsilon t, right? And then I add that one with the corresponding coefficients into my x0. It's going to give me xt, right? So that epsilon t is exactly that one, the direct noise, right? This is not the noise which I got from xt minus 1. That is different, right? Everybody's cool, right? Clear? So the point here is that what I'm getting here is eventually xt minus this guy, right? And now, what you can say when you look at this guy, you have your xt, right, which is your noisy data, right, noisy sample. And then you are computing something in terms of the noise you added to it to make it data, noisy data, right? You subtract that one from your data, right? So this is eventually denoising, just subtracting the noise from your own data, right? So what is eta t? Eta t is indeed denoiser of xt, right? And what your model is doing, that mu, is trying to look like eta, right? When you are training your model mu, the mean value, is trying to be exactly like eta. This is why we call it denoiser. Because this is trying to be exactly the denoised version of your xt, right? So it gets xt at time t, and then it tries to just denoise it. Everybody's clear? Yes?
What is the meaning of one?
The coefficient?
Yeah, the coefficient.
I'm going to tell you in the next slide. Yeah. No worries. But right now you get that we are just getting the data, noisy data, and we are subtracting it, subtracting some noise from it, right? And this is the noise that we just added when we wanted to make the noisy data, right? Somehow. But we are not exactly subtracting that one. We're subtracting some coefficient of it, right?
I assume that the coefficient is something that, because you sample the epsilon from a normal Gaussian distribution, right? So you need...
That is the one, yeah. But when you are making the xt out of x0, you don't multiply with this coefficient. You multiply with square root of 1 minus alpha bar, right? But you are not subtracting that one, right? You're subtracting a scaled version of it. Why we're doing it, I'm going to explain it, okay? But everybody now is clear that eta t that we had in the DPM is eventually a denoised version of xt, right? So it looks at the xt, it knows what is if it knows what is the noise, then it's going to subtract it with some coefficient from xt, right? Okay, cool. Now that you see this one, now let's try to do something else. What is the idea now? Is that now I'm thinking about the forward diffusion, okay? When I am just moving on the forward diffusion every time, I multiply whatever I have. It's not the data itself anymore, right? I started at time 0. I kept on going till I got to xt minus 1, right? I multiply it with some square root of alpha, right? And then I add some noise, correct? Everybody's clear? So this noise, I'm showing it by epsilon tilde. I'm not showing it by epsilon. The color is also different. One question, Is it exactly, is it the one which we had in the previous slide? No, this is not the noise of the direct path, right? So the noise of the direct path was the noise which was, accumulation of all of the noise you have added from beginning of time, right? But since we do know how we can explain the direct link statistically, we could sample from it, right? Everybody's clear, right? So key point here is that this epsilon tilde is not same as epsilon, right? They are not the same process. But they are correlated, of course, right? Because a part of epsilon t, the red one, is epsilon tilde, right? So epsilon tilde here, and epsilon tilde t minus 1, t minus 2, till epsilon tilde 1, that you added all of them, right? All of these guys together make epsilon t, right? The one which you can write down in the direct path, right? Everybody's cool? You got the idea? Yes? Okay. Now, these are not the same thing. This epsilon t is the one which you have in direct link. The other one, but they are correlated, right? Now, say that I do know what is epsilon tilde. Say that I do know how much noise, what is exactly the noise sample I added to my previous time to make my Karen noisy version. If I do know that, how can I get from my Karen noisy version back to the previous time? Can I go? I just do the math, right? I would say, okay, xt minus 1 going to be, I take this guy to the other side. So xt minus this square root of 1 minus alpha times epsilon tilde. So I took the other guy, this guy the other side. And then I divide everything by 1 over the square root of alpha, right? So this is the deterministic, explicit, reverse move that I can do if I did know what is epsilon tilde, right? But I don't know it, right? Now, what I'm doing with this eta t that you saw that we just derived in the other slide, we are eventually estimating this epsilon tilde. What we are doing, the epsilon tilde, we don't have it, right? Because if we want to have it, we need to sample every single time, right? And this is not possible. We're just getting rid of the time by time sampling, right? Every time that we want to do generation, we're going to just generate the noise, the direct noise immediately, right? But the key point here is that we can estimate somehow this guy out of epsilon t with this formula, right? Because that epsilon t, I mean, you eventually added, this is the fraction of the variances that they have, right? One of them has 1 minus alpha, the other one has 1 minus alpha bar, right? And if you think about this kind of estimation and you replace it here, so I had this expression, instead of epsilon tilde, I am going to just replace the estimation of the time noise, right? It's estimation. If I do that, if you replace that one, you're going to end up with this expression. And this is exactly the eta t that we computed. So now, do you have the feeling what this eta t is? What the eta t is that is looking at time t that you are, right? You do know what is this direct noise. Why you do know it? Because you sampled it when you wanted to make this noisy version during your training, right? Everybody's clear? So when I want to make xt when I'm training my network, I'm going to sample 1x0. I sample one noise epsilon t, and then I add them correspondingly, right? Now that I made this one, now I want to know how I can get back from this one, not directly to the beginning of time, because this is a huge noise. I cannot handle it, right? I just want to know how I can go one time step backward. Now, the thing that I'm going to do, I'm going to use epsilon t, the direct noise, to estimate how does the time noise, epsilon tilde, going to look like, that tiny noise. I'm going to use this one to estimate that one. Now that I estimated that one, I just move backward, right? So I'm going to say whatever I am minus the variance times the particular noise that I have at that time. I just subtract it, so I'm going one step backward in time. Right? Everybody's cool? Questions? So you got clear what this eta t means, right? So eta t is eventually the best thing somehow you can do to estimate what was your previous time. That's it, right? Okay, so if you got clear about that, now let's get back to the sampling and see how the sampling was. The sampling was that I look at the output of my neural network. I subtract it from this eta t, and this is going to give me the loss at the particular sample x0 and time t, right? And this eta t, if I want to compute it, this is going to be exactly this expression, right? The one which I showed you in the previous slide, right? So what you do when you are training, you are going to sample one x0, right? Also, you sample one epsilon t, right? Out of this x0 and epsilon t, you can make your xt, right? Out of that xt, you can compute your eta t. You put it there. You can also put xt inside your neural network. You get the output, and then you try to minimize that one, right? This is what you are doing when you are doing the training, right? Everybody's clear? Now, but the key point here, one nice observation is that, as I told you, when we are training DPM, since we are building xt at every single time, we do have access to epsilon t, right? We do know what is exactly that noise, because we made it, we sampled it to make, right? So since we have that one, then we can eventually use it in our training. Now, this is the one which makes the idea of DDPM. What does DDPM say? It says that maybe we can put this the average network to be exactly same as this eta, the denoiser that we have. Yeah? The only thing that we want to learn is what is this epsilon, the noise term, right? Maybe we can think of the mu network in this form, right? So it means that I have the particular value of xt. So when I have xt, I make one noise network. This noise network, what it does, it looks at xt and time and tells me what was the direct noise I computed when I wanted to get from data to this point, right? Right? Now that I have this estimate, epsilon w, then I just put it inside this expression. This is going to take me from that time one step back, right? So maybe I can use this network. Maybe I can put my model to be this form, right? So I don't think of mu to be general network anymore. I just think of it in this form. Now looking at this one, the only guy who is being modeled computationally is the noise estimator, right? Rest of it is the things that you have, right? Everybody's clear? Now if you are clear, what is the output dimension of this epsilon? So if you think about the epsilon noise, the guy who is learning the noise, it's taking xt, one noise is sample, time is step, and it gives you one estimate of the noise at time t, the direct noise. What is this guy? What is the dimension of the output? The same as the data, right? It's exactly the same as data. Again, this is why in practice you usually use UNet, right? Because you want to get the noisy version. And now instead of learning or recovering the data sample, you are recovering the noise, right? But it's no problem for you because you do have both noise and data sample when you are doing the training, right? You sampled your own. You have x0, you have epsilon, right? This time, instead of recovering x0, you are recovering epsilon, right? Who cares? Everybody's clear? So this guy in practice is typically, I mean, most of the time, this is a UNet, right? This is a UNet. And this is what you see in most implementations. Questions? Yeah.
Sorry, in DPM, we're assuming that the epsilon is from union Gaussian, right?
In all of them, we consider the true epsilon is coming from uniform Gaussian. In all of them, yes.
But in DDPM, we're actually estimating the noise.
No. I mean, I'm going to show the training loop, but what we are eventually doing, you have the sample, right? You have epsilon. This is coming from Gaussian, right? Yeah. And then you have one network which is magically able to look at the noisy version and give you that Gaussian sample. Yeah, maybe we go in the next slide, you're going to get it more clear, okay? But right now, the thing that is that the only thing that you computationally model right now is this noise term, okay? So you want to look at the noisy version, but you don't want to say what is the data. You want to say what is the noise that was added to data. You just want to know that one, right? Okay? Questions? No question? Okay, cool. So if you got no question, then maybe you can go ahead and replace everything inside the expression for loss, right? The sample loss was mu minus eta, right? And then I'm going to replace mu and eta by the expressions that we had, right? If you look at these expressions here, mu and eta here, they're both exactly the same thing. All the coefficients, everything are the same. The only difference here is that I have the sample noise epsilon t. This is coming from a Gaussian distribution, right? Here, I am replacing the output of my neural network, right? And what I can say eventually that this difference is going to only contain this guy, right? Anything else is going to be 0, right? And the difference between mu and eta is going to be a scaled version, so I'm going to call it omega bar, whatever, of the difference between the noise output and the sample noise. Noise network output and the sample noise. You got it now? Yeah. So when you are sampling, when you are training, you first just sample one data sample, right? You sample one Gaussian noise, right? And now the thing is that you give this you combine them to have your noisy version, right? You give the noisy version to noise network, but the output of the noise network, you want it to be exactly like this Gaussian noise, right? This network is now able to look at your data and tell you what was the noise you added, right? So now that you have the noise, you can subtract it from your data, right? Not worse. So everybody's clear? Questions? No question? Okay, great. So this is something that you can easily compute because, as I told you, you have xt and you have epsilon t as well. These are the things that you are sampling. The intuitive illustration is that you have one model which is able to estimate the direct noise looking at your noisy data, right? So it's going to tell you what is the direct noise or the noise that you added to your original data when you were making this noisy version, right? And now that you have this one, you use this direct noise to estimate the previous time step, right? You just go one step backward in time. Everybody's cool? Questions? No question? Okay, great. So if you got no question, then this is going to be the way that you are going to compute the risk. Again, this is eventually same as the one which we had for DPM, but this time our network is only computing the noise, right? So it's worth going through it together. So I am going to sample one single data sample, one single time sample is okay. Now I am going to sample one noise, right? This noise is the direct noise, right? The noise which I'm going to use to make my xt out of x0, right? This is the one which at the end of the day I want the output of my neural network to look like, right? So I'm going to get this sample noise. I am going to compute my noisy version. So this is xt, the sample xt that I did. Now that I have this one, I'm going to pass this sample xt through my neural network, right? This is going through the neural network. At the output of the neural network, I get something which I want it to be an estimator of the sample noise, right? So I want the output, this epsilon hat that I have at the output of the neural network, to look like exactly like the sample noise that I sampled, right? So I sampled epsilon. I made xt. Now I want the output of the neural network to take me back to that epsilon, right? So I'm going to compute this loss. Now, I have a neural network. I just went forward. I just back propagate to compute the gradient. That's it, right? I have the gradient. I have the loss. So you can just average the loss. You can average the gradient to have your batch gradient and your batch loss, right? Everybody's clear? Okay. cool. Now that you have computed this one, then you can simply train your DDPM, right? So your DDPM eventually contains one network. That one network is only learning noise, the direct noise that you need to add to your data to get to your noisy sample at time t, right? So you're going to make multiple batches. Every single batch, you just compute the loss and gradient over that batch, exactly like what we did in the previous slide. You update, right? And you keep on going till your model converges, right? Questions? No question? Great. So if you got no question, let me also just explain how we can do DDPM generation. So the generation is the same as before, right? The only difference now is that your mu is explicitly given in terms of xt and the output of the noise network, right? So the thing that you are going to do, you are going to sample one noise sample, and then you're going to make noisy version of your data. So you're going to just, you have the noisy version, so you're going to get xt with the time index, you pass it forward. You're going to get an estimate of the noise. Now that you have the estimate of the noise, you put it exactly in the expression that I told you. So your denoised version, x hat, of the previous time is going to be this epsilon t here, subtracted from xt, multiplied with this. This is the exact term that we had for the model, DDPM model. And then we're going to get the previous time, right? Now that I have the previous time, remember, this was the mean value, right? So you still need to add some noise, right? Don't forget that. When you are doing DDPM, you're still adding some noise, right? Because the one which we computed was mu, right? Mu was the mean value, right? You still add some noise. Clear? So you're going to add some backward noise, and then you're going to keep going backward in time till you get to the beginning of time, right? Everybody's cool? Questions? Yep. Yes? Yes. Not forward in time. I'm forward in the neural network. I mean,
Oh, I see.
Yeah, forward propagation. I mean, sorry. Yeah, maybe it's confusing.
Okay, so then, essentially, like during sampling, we're just doing the denoise.
Exactly. Yeah. Indeed, I mean, in practice, you never do the noising, right? You never go forward in the trajectory at all, neither in training nor in sampling. Even though you think about that, but you don't do it really, right? Because every time that you are training, you just sample one time, you just directly jump to that time, get your sample, you train, right? And then when you want to do sampling, you don't really need to go forward, right? You just move the reverse trajectory, right? Yes?
So given that we are still adding noise when we do inference or sampling,
Okay.
how do you evaluate the performance of this against GAN or?
Yeah, this is going to do much better than them. This is the whole reason that they are now trained. But there is also a way to get rid of this one, which I am probably explaining next session. This is what we call a DDIM, implicit only for sampling, not for training. Okay? But like in the basic proposal, epsilon is still here. Sorry, sigma is still here. And that noise, if it's not there, is going to destabilize your sampling process. Unless you do the DDIM, which is a more stable one. So everybody's clear? So let me just give you a quick, just a few implementational notes here. And then we are over with this one, which is mainly over with this chapter, a tiny section. I'm going to finish it on Tuesday. So one thing is that those omega terms, right, the one which is just getting multiplied to your time loss, right? That one is usually you just throw it away. You can keep it. You can make it like perfectly the one which you add in the expressions, but it's not going to really impact that much, right? Because at the end of the day, you have so much of noisy samples that that tiny bit of weight is not going to do so much for you. So in many practical settings, we said that omega bar equal by 1, but there are works where people try to just be very accurate about that. It's not like you drop it all the time. So one other thing is that this sigma, I told you that this is something predefined, right? You can come up with your own idea. That's totally fine. in the basic approach, it was suggested that you use exactly the same variance that is considered in the forward diffusion, right? So like every time how much forward diffusion was added, you just use the same variance. It was the initial proposal, but which means that you are going like in forward and backward direction with the same variances. But there was one tiny difference, and that was that when you get at the last sample and you want to get your data sample, you don't use any additive noise anymore, right? So in this loop here, when you get to time t equal by 1, like this is x hat 0, you don't add any noise anymore, right? So you don't have sigma 1. Sigma 1 is eventually at t equal by 1, sigma is set to be 0, right? You can guess. You don't want to add noise to your last sample, right? Like the one which we had in VAE, right? So you don't want this to happen. And one thing else is that this alpha t, so as I told you, this is just a predefined again. And this means that you need to have some expression which is explaining how alpha is going at every single time step, right? So classical one, basic one again, is the linear one, meaning that you're somehow considering one slope and one bias, and each time you're